Hello, everyone, and I am back. And in this lesson, we start talking about something new, which you'll see this chapter, which is optimization problems. How do you get the best or worst out of something, maximize and minimize it? So since we're talking about optimization, which is about maximum minimums, let's recall what those mean. So f of x will have a local maximum. And to help you visualize that, picture a maximum is a point at the top of a peak like that. When the derivative is 0, as you'll see it, the slope is 0, and the slope is changing from a positive slope to a negative slope. And changes from positive to negative. Right? And then similarly, f of x has a local minimum. So picture a minimum here where the slope is 0 and the slopes are changing from a negative slope to a positive slope. So in words, that's when f prime of x equals 0 and f prime of x changes from negative to positive. Okay. Now, we're going to understand this optimization problem through an old example, and this is one from Mr. Palmer's class that is one of his bigger problems, and hopefully you're not too scarred from it. And that is, how do you maximize or the volume of a 8 by 5 by 11 inch piece of paper by folding up the sides. So it's not the exact worded question he would ask, but it's the same idea. And I'll kind of talk you through about what you used to do in his class and what you can do now with calculus. So the idea is, if you have an 11 by 8.5 paper, well, what's the maximum volume you can make out of it? When I say maximize volume, picture like an open box, right? Where you would cut slits into the corners to make the height, so which allows you to fold it up into this open box. Well, the height, we don't know what it is, so the height will be x. And the length will be 11 minus 2x, because if we cut away these two parts and fold it up, well, that's 11 minus both of those. And the width, similarly to how we got the length, would be 8.5 minus 2x, taking away each of those cuts as you fold it up. So hopefully that is some resemblance to what you remember doing in his class. Now, in his class, so before we even get there, so the volume of this box can be represented by x times 11 minus 2x times 8.5 minus 2x. And in Palmer's class, the way you found this answer was through the graph or table. Well, what you would do is you would go into your calculator and you would put this equation in, x times 11 minus 2x times 8.5 minus 2x. Now I'm going to change my windows right away, and I know where it's going to be, so I want to make sure it shows. And from a graph, you would say, okay, well, that's going to be a cubic function when you simplify it, and there's our cubic, where at that point, that's your max. And you could go to your table and find that, or you can just use the calculator feature and say, what's the max there, which I put a max of bound at 0, a right bound over there, where my guess is somewhere in the middle. It tells me that my max is going to happen at x equals 1.585 and y is 66.148 as your volume. And that's what you were able to do in Palmer's class. Now we're at a point where we can do this same problem, but using calculus, which will help us a little bit more than being able to do a graph table. Both options are good, but it's another way to learn something. So I'm going to rewrite this velocity problem first as a polynomial. If I multiply this out, you would have 11x minus 2x squared times 8.5 minus 2x. And if you multiply that out, our volume equation would be 93.5x minus 22x squared minus 17x squared plus 4x to the third. So I'll write down here in this method here, rewrite it with the highest power first, where I'm going to combine those two and put negative 39x squared So that's our velocity equation. Now using calculus, we can find the maximum, recall, by looking at its derivative function, its derivative. So if we look at the derivative here, that's 12x squared minus 78x plus 93.5. And remember, recall that fx is looking when the derivative is 0 and it changes from positive to negative. So now we have to know when is this equal to 0, find its critical points. And at this point, you know what you can do is, unless it says no calculator, you either use the quadratic program on your calculator, and if you don't have it, just Google or YouTube it. It's all over, and you can find it and just copy down the steps. I'll put YouTubeable. Sorry about that. Right. Or, you know, you can use the graph on your calculator, which is what I'm going to do here. So let's find the zeros of this. So we go to y equals and put this equation in. And then we go to our graph. And all we need are the zeros. So what we're going to get here, I can see them there. And you have a 0. Do my left bound at 0, my right bound at 2, because I see it happens before 2. Guess right to the left of that. So I have one 0 at 1.585, and I have another 0 at, let's guess my left here, my right there, in the middle of those, at 4.915 approximately. And then if we understand the intervals or even keep this calculated, we can see that before 1.585, it's positive. Or if you plugged in a number before, such as 0, that would make that go away. We're left with a positive number. A number in between here, notice the function is negative, or you can plug in a number such as 2, and you get a negative answer there. And then a number afterwards, you are positive. So what we have here from what we know in calculus is that these are zeros. And notice it's changing from positive to negative, changing from positive to negative. So right here, there is your local maximum. And similarly, that is your minimum when you'll get your lowest possible volume size box, which is interesting too. So we could say then, answer the question, what's the maximum volume? Well, if we cut this paper by 1.585, so if x is approximately 1.585, well then your volume will equal, and we plug that in, so V of 1.585 is equal to, let's see, put that in a calculator, 1 times 11 minus 2 times 1.585. And then 8.5 minus 2 times, a lot of 5's going on there. And what we get is 66.148, which notice, just to show you, I got the same thing we got from the graph and table from before. And that is using calculus to find the maximum, right? By understanding that we can just look at its derivative, its rate function. So there it is, optimization problems. Now yours will be slightly different than this, but the idea is get an equation in one variable, an equation in terms of one variable, and then look at its derivative, and then look at the derivative function. And that will help give you your maximums if you just look at 1 and 0 and change this from positive to negative. Very awesome. You know, recalling all the way back from Mr. Palma's class of Palma you would do, and now looking at it through a new lens that you know how to do now, calculus. All right, good luck on your assignment. Let me know if you need any help. Bye-bye.